How do we know the age of the solar system? Well, we have at our disposal the method of radiometric dating, which basically is based on the following. Certain nuclei are unstable and they undergo a transformation with the emission of, say, alpha particles. These are the nuclei of helium or electrons and or gamma rays. And they transform into another nucleus, so-called daughter nucleus. So the original radioactive nucleus is referred to as a parent nucleus, and the final product is referred to as the daughter nucleus. Now, if you have a number of these parent nuclei, we cannot tell with certainty when any one of them will transform into a daughter nucleus, because it is a random, it's a stochastic process. However, all we can definitely say is that if we had a large number of parent nuclei, we know the time it takes for half of them to transform into the daughter nucleus. We don't know which ones will do that, but if we start with a large number of these nuclei, then after this so-called half-life of the nucleus, exactly half of the nuclei will be transformed. So I tried to illustrate that in this series of drawings. Suppose we have a rock, and when the rock was formed, we had certain number of parent nuclei. And just for the sake of argument, so that we can follow the argument more closely, I have 16 these red dots representing the parent nucleus A. Then after half-life, exactly half of them will transform into daughter nuclei. So after one half-life, we'll have half of the nuclei will be still untransformed, parent nuclei, and half will be the daughter nuclei. So underneath here is a pie diagram representing a percentage of parent nuclei. So we start with 100%. After half-life, we are left with 50% of the initial number, and the remaining 50% are daughter nuclei. Then, after another half-life, half of these remaining parent nuclei will transform into the daughter nuclei. So now I'll have only a quarter, half of this amount here of parent nuclei present, right? And yet, after another half-life, I will have half of parent nuclei present here transform into the daughter nuclei, right? So I'll end up with 12.5% of the original number. So I'll ask you to think about what is the percentage of the parent nuclei after 4 half-life. And I'm sure you can guess what the answer is. So then we have a method for dating of rocks, and that is compare the relative amounts of parent and daughter nuclei and deduce the age of the rock based on the half-life of a parent nucleus, right? So if you take a piece of rock and you find that 12.5% is the parent nucleus and everything else is the daughter nucleus, then you know that 3 half-lives have passed since the rock was formed, right? And therefore you can say how old is the rock. So here I give several of examples. I mean, the list is much longer for practitioners of the method, but I'm giving a few highlights. First of all, carbon-14 transforms into nitrogen-14 with a half-life of 5,730 years, right? And this can be used to determine the age of objects made out of organic material into which carbon-14 is incorporated over the periods of times of several thousands of years, right? Then we have potassium-40, parent nucleus transforming into argon-40, and the half-life is 1.25 billion years. The next one is uranium-238. The end product, the daughter nucleus, is lead-206, and the half-life is 4.47 billion years. Thorium-32 transforms into lead-206, and the half-life is 14 billion years. So you see that there are tremendous variations in scales. Rubidium-87 transforms into strontium-87 in 48.8 billion years, and samarium-147 transforms into neodymium-143 in 106, with a half-life of 106 billion years. Okay, so we have quite a range here of half-lives, and then you don't stick to a particular radioactive nucleus, but you try to achieve consistency with several of them, right? So the results of doing this radiometric dating is that most on the Earth, most old rocks are between 2.5 and 3.8 billion years old. And as it happens, the Earth's oldest known rocks are here in Canada and are 4.031 plus or minus 0.003 billion years old, right? This is the result established in 1999. And then quite recently, I mean, this was known for a while, but most recent dating was done just not that long ago. Within a month or so, I read an article on the BBC Science page that there are isolated crystals, not complete rock, that are 4.4 billion years old, and they are found in Australian Shield. So based on these numbers, we can definitely say that the age of the Earth is at least 4.4 billion years. Could be older, but we don't have material that is older than this. Okay, so it's at least 4.4 billion years old. The rocks that were brought back from the moon after various Apollo missions, their ages range from 3.16 to 4.5 billion years, and it depends on where the samples are taken. Lunar Maria, those dark areas, which basically are the areas where impact craters got filled up with hot magma once moon had molten interior. They are about 3.16 billion years old, and the samples from highlands on the moon are 4.5 billion years old. Now, meteorites are all 4.55 billion years old. So you see that all the numbers are close to 4.5, 4.6 billion years. And then, as I've mentioned earlier, based on our understanding of solar physics, using so-called standard solar model, one can calculate the sun's age based on its mass and the current energy output, and the result is about 4.6 billion years old. So all these numbers, and you see they are quite independent, samples come from different bodies in the solar system. We also can estimate the age of the sun, that all this points to the solar system forming some 4.6 billion years ago.